cut one of those off back there if you want. Maybe both. Check. It's kind of bright. It's cut them both off. Let's see. It's not too dark in here. I don't like cutting them off and it be dark, but the windows are pretty light today. Okay. All right. So, if the order does not matter, like in the fruit salad, if you make fruit salad, it typically is not going to matter whether you put the apples or the bananas or the grapes in first, right? Doesn't matter. You're just putting it all in a bowl and mixing it up. So, if the order does not matter, it's a combination. Okay. However, if the order does matter, it is a permutation. So for that combination for your lock, if it's just a simple number lock, whenever you put in 3, 4, 8, it will open. If you put in 8, 4, 3, it's not going to open. Right? It's got to be in order for that to unlock. So the combination to your lock is really not a combination. It's the permutation to your lock if you're using mathematical terms, because the order of that matters. So we are going to look at how to figure out how many different combinations or permutations that you might have for whatever specific set of variables that we're looking at. There are 4 different types of things we can have. We can have a permutation, which means order matters, where repeats. Sorry. Good gracious. Are allowed. We could also have a permutation where repeats are not allowed. We could have combinations where the order doesn't matter and repeats are not allowed. And we could have combinations, order does not matter, where repeats are allowed. Okay. These 4 are in order from easiest to most difficult. Okay. So the easiest thing you can do is have a permutation where order matters and repeats are allowed. Okay. I should have specified when we were doing our lottery that we did at the beginning of class, I was going to say that order mattered, right? And repeats were allowed. You could choose A or B if you wanted to. So that's the situation that we were dealing with there. So let me change this so it's bigger. Okay. So in that case, we had 26 options for the first letter. We had 26 options for the second letter. And order mattered. So let's look at this situation. We are going to create a 2-letter code using the letters in the word fox. Letters can be repeated. How many codes can you create? So, like, if I write these down, you could have F and F, because repeats are allowed, right? I could have F and O. I could have F and X. Then I also could have O and O, O and F, O and X. And I could have X and X, X and O, X and F, right? So, in this case, there are 9 different letters that we could choose. Now, if I'd offered this to you in the lottery, that wouldn't have been too bad of a deal, right? You would have possibly been able to get that. So, you can find the amount of codes in this case by doing the number of options for the first letter times the number of options for the second letter, which in this case is just 3 times 3. Okay, so there were 9 options, right? So our lottery we did at the beginning of class, that was the same deal. We had 26 options for the first letter and 26 options for the second letter, and it was fine to repeat. So 26 times 26 gives you the 676, I think, Philip. So there were 676 different possibilities that you could have gotten there. So if you entered one time, you had a 1 out of 676 chance of winning. Okay? All right, so the shortcut rule for this, okay? For all of these, we're going to have formulas. I personally only use the formula for the very last hardest one. I think through it logically, sort of, for the others. And in order to do this, not yet. All right, so the size of the sample space and the sample space is all of the possibilities. So like for this one, it was FF, FO, FX, all of those possibilities. So the size of that sample space is n to the r power. And in this case, n equals the number of items to choose from and R equals the number of items chosen. So in this case, I had 3 different letters I could choose from, and I chose 2 of them, so I'd do 3 to the second power, which would give me 9. I always just think number of options for the first times number of options for the second. But you can use this formula also. Okay? Questions? All right. Okay, so let's talk about permutations where repeats are not allowed. Okay, so same situation. We're going to create a 2-letter code, and I chose this because it's so small that we can actually write out all the instances here pretty easily, that the letters cannot be repeated. So we cannot have FF, but we could have FO or FX. We cannot have OO, but we could have OF or OX. And we cannot have XX, but we could have XO or XF. Okay, and order matters here, so FX and XF are not the same. Okay, so in this case, we've got 6 different possibilities. We could have also just taken the list we had for the last one and mark out all the doubles, those 3 doubles that we had there. All right, so in this case, we can find the amount of codes by doing the same thing we did on the last one, number of options for the first letter times the number of options for the second letter. Okay, now that looks exactly like what I wrote down for the last problem, but here's the difference for this situation. since we cannot have repeats, I have FOX. I've got 3 letters to choose from for the first letter, right? How many letters do I have to choose from for the second? I've got 2 because of all, like let's say I pick F. I've already picked F, so it can't be used again. So there's only 2 other letters I could pick. So I'd have 3 times 2, which would give me 6 in this case. So for example, with that lottery, if I had made it where you cannot repeat, then you couldn't pick A, or B, B, then instead of being 26 times 25, 26 times 26, you'd have 26 times 25. Because once you pick A, it can't be used again. You only got 25 letters. So you'd have 650 for that. So that would very slightly improve your chances of winning if you can't repeat a letter, right? But only slightly. Still probably not a great deal to play that lottery. So now the shortcut rule for this is probably going to have some stuff you haven't seen before. So size of sample space. Okay, and so the size of the sample space is going to be this. Make sure I got it right. You guys seen that before? Not in math anyway. Have you seen it, Kayla? What is it? So like if I had 5 with that exclamation mark, do you know what that would be? Okay, so that exclamation mark is called a factorial. If Coach Wood comes by and sees this on the board, almost guaranteed, he's just going to yell 5 really loud because that's what exclamation marks mean that you're supposed to do, right? Just so, nah, but guaranteed he would do it if he walked by. Because anytime I ever have a factorial on the board, he just sticks his head in my room and says whatever number it is really loud. Just yells 3 really loud. But this is not English, this is math. So factorial means that you do this. 5 factorial means 5 times 4 times 3 times 2 times 1. So it means a number multiplied by all the integers below that number until you get to 1. Okay, so if it was 100 factorial, it'd be 100 times 99 times 98 times 97 times 96, all the way down to 1. There is a button on the calculator that, well, there's not a button. Where'd my yellow one go? But there is a way to do this on your calculator. So if you will everybody look at your calculator because I can't show you on the screen. And I have to remember where it's at. I know one way to get it, but I can't remember the quickest way. We're going to have to go catalog, maybe. Okay, no. All right, so probably the quickest way to get to this on your calculator is to go to Math, and then hit the over button till you get to PRB, which is probability. Okay, and number 4 right there is the factorial, although you have to have a number in first. So like you need to do, if we want to do 5 factorial, we would do 5 math, go over to PRB, and number 4. So 120. Okay, everybody make sure you can do a factorial in your calculator right now. If you can't, ask one of your neighbors. Make sure you can get to it. Yeah, if you try really big numbers, it's going to shut your calculator down and it's not going to be able to do it. So it'll say, if it says overflow, it means I can't do it. It's too big. So, yeah. You can't do factorials on this? No. Factorials are only for integer values because I don't think the calculator would do it. It did? Oh, wait, hold on. I do not know what a factorial of a decimal means. I do not know how that's calculated. Because like 2.5...
And we'll do 0.4.
Would it be...
0.4 is
It's probably because the decimal got too small. Let me try something here. Let's try 0.9. Let me see if I can tell what it's doing.
I'll let do 0.5, but it won't do 0.6 or 0.4.
Let's try, let's see, 1.5 math. Let's see if we can figure it out. Uh-oh. 0.5. I might have an idea. Okay, let me try it. No. I have no idea what a factorial of a decimal means. You do not, I'll look it up and let you guys know if I can figure out the answer, but you do not need to know it for what we're doing because you will not be doing factorials of a decimal. That will be all whole numbers for this. So, like in this particular case, the same thing is true of what we said earlier. N is the number you have to choose from, and R is the number you're choosing. So in this case, you would have 3 factorial over 3 minus 2 factorial, which if you think about, instead of using your calculator, it's 3 times 2 times 1 over, and 3 minus 2 is 1, so 1 factorial is just 1, right? And so in this case, the 1's cancel, but I mean, it's just the 1, so it doesn't even really matter there. So you end up with 3 times 2, which is 6. I think these are easier to do without the formula because generally what you're just doing is number of options for the first times number of options for the second. That's what the formula does, which is easier to me to figure out. But this is the formula if you so choose to use it. And eventually we're going to need a formula for something. Okay? So there are 52 cards in a standard deck. All right, so we got a couple questions here. You'll see a lot of card questions because cards are generally used a lot for probability. If you don't believe me, you could go to Vegas. There's going to be a lot of cards there, right? I've never been, I don't know if it'd be the place for me, but pretty sure it would not be the place for me. But so you draw a card from a deck, you replace it, and draw a second card. How many possible outcomes could you have? So how many options do you have for the first card? You have 52. How many options do you have for the second card that you draw? You replace the card. 52, because you put that card back, so it's still 52. So 52 squared, or 52 times 52, is going to give you 2,704. So if I had you bet your bathroom passes on this, that'd be even worse than the 2-letter code, right? Okay. If you draw 2 cards from a deck without replacing the first, so you're going to draw one, keep it, and then draw a second one, right? This time, number of outcomes is going to be 52 times 51, because there's only 51 cards left. You've already pulled one out. So 52 times 51 is 2,652. Slightly increases your chances of getting the correct whatever you're looking for, but not by a whole lot, right? So these are permutations. These are where the order matters. First card, second card. All right. All right. If you roll 2 dice, how many possible outcomes can you come up with? So you're rolling 2 dice. We've already done this sum, 6 times 6, which will give you 36. Okay. All right. Here's another one. Jose competes in a 5K. There are 25 other people in his age group. The top 3 winners receive cash prizes. How many different ways could the cash prizes be awarded? Okay. So in this case, we're going to assume they're given first, second, third place, right? And that probably first place gets more money than second place, and second place gets more money than third place. So does order matter in this case? Order matters because, you know, if you're not first, you're last. Here, you got the order matters, right? So if you're second, you're not as good as whoever was first. If you're third, you don't get as much money. So order matters. Can you have repeats? Okay. Aaliyah says no. Is she right? Okay. We can't have repeats because if Jose wins first place, he can't also win second place, right? So there cannot be any repeats. So now, in a race, of course, races are not randomly decided. Somebody wins it because they have more skill. But let's say that they are randomly decided. How many options do you have for the first place? 25 different people could win first place. You're right. It should be 26. Thank you. Smart thinking there. Very good. That's tricky. I don't even think I meant to be that tricky. I did the answer wrong on the answer key that I've got right there. Okay, but you're right. 25 other people would be 26 altogether. So, so we've got 26 people that could win first place. How many could win second now? 25, because somebody's already won first, and that person can't be second. And how many for the 24? So if we do 26 times 25 times 24, we're going to get 15,600. I don't know about you guys. I love probability. Sometimes it gets a little confusing, but I think it's like probability is crazy because what you think you have a pretty good chance of, a lot of times you have no real good chance of. So there are 15,600 different ways that people could win first, second, and third. So if you were trying to come up with these, like if you thought, oh, I'll just list them out. I'm not going to use any math. I'm just going to list them out. You'd give up on that pretty quick, wouldn't you? After you realize, hold on, this is not going to work. So tons of options here for this. Okay. All right, let's look at the next one. Combinations with repeats not allowed. This is your next most difficult. Okay. These combinations are more difficult than permutations. If order matters, it makes it a little bit easier. Okay. But if order does not matter, then it makes it more difficult. Okay. So I've got us a simple one here so that we can actually list out the possibilities. So there are 3 blocks in a bag. You choose 2 blocks without replacing the first block before you draw the next one. How many different ways can you choose the 2 blocks if order, hold on, I should say does not. Oh, wait, no. If order matters. Yes, I do mean this because the next part's going to ask you. Let me read and make sure. Okay, so this is not a combination. This is a permutation. So let's assume order matters. I'm just going to call the 3 blocks 1, 2, and 3. All right. So you could choose 1 and 2. You could choose 1 and 3. Let's see. We are not replacing it, are we? Without replacing, no. So you can't get 1 and 1 because once you pull 1 out, you got to get 2 or 3. And so we could also get 2 and 1 or 2 and 3. And we could also get 3 and 1 or 3 and 2. Now, this is if order matters. This is the simpler case where order matters. So you've got 3 options for the first one and 2 for the second, which gives you 6 altogether, right? But if you are just choosing 2 blocks, it might not matter what order that you choose those blocks in. So if we are doing this, how many different ways can you choose the 2 blocks if order does not matter? So basically what I want to do, let's take what we just had, 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. This is what the order mattered here. And let's mark out any that are repeats. So I've got 1, 2, I've got 1, 3. Those are different. 2, 1. Is that any different than 1 and 2? If order doesn't matter? Nope. Okay. 2, 3, that's new. 3, 1, is that the same as one we already have? Same as 1, 3, so let's mark it out. And what about 3, 2? Same as 2, 3, right? So your only real options are 1 and 2, 1 and 3, and 2 and 3. So you only have 3 options here. Now, if I'd given you those odds, you got a 1 in 3 chance of winning for the lottery. I'd probably bet some of my bathroom passes for that. Okay, so we can use the same method for finding number of outcomes as permutations without repeats, except we must reduce it by the, make sure I'm getting this right, the number of ways the object, number of ways the object can be ordered. Okay, so this one, I told you that we're starting off with the easiest. Permutations are the easiest. So if order matters and you don't repeat, you just multiply. If order matters and you can repeat, just 26 times 26. Order matters and you cannot repeat, 26 times 25. In this case, we're going to do this. I'm going to write it 2 ways. Okay. I realize you don't quite have room there. We could do number of choices for the first times the number of choices for the second divided by the number of ways to be in order. Okay, so like for this particular instance, you have 3 choices for the first block. You are not replacing this, so you got 2 choices for the second block, right? And so how many ways can, like, let's say block 1 and block 2. How many ways can you put block 1 and block 2 in order? 2. You could have 1, 2 or 2, 1, right? So you got 2 ways to put those in order. Well, whenever you do this, you get 6 over 2, or those 2's can just cancel out there, and that's going to give you 3 ways for this. Okay, the formula for this, if you want to use the formula, because this is getting a little bit harder to reason through. I still usually reason through this one, but some students prefer just to use the formula. The formula for this is that your size of your sample space equals n factorial over r factorial times n minus r factorial. Now, if you look, this part right here, n factorial over n minus r factorial, that's your permutation rule, right? That's your permutation where repeats are not allowed. So that is the 3 times 2 part. The number of ways that these can be ordered, that's your r factorial. So in this case, we were picking 2 objects, so 2 factorial is just 2 in this case. But if we had bigger, like we were picking 3, we would do 3 factorial there. In which case it'd only be 1 because there's only 3 blocks. But okay, so let's look at an example. Okay, so in a lottery, you must choose 3 numbers that range from 1 to 30. You cannot choose the same number twice. If your 3 numbers match the 3 numbers chosen in any order, you win. How many different lottery tickets could you buy? Now, we're working our way up to the real lottery, like if you're thinking Powerball lottery, because in Powerball lottery, you have 5, well, Powerball's a little bit weird, because Powerball, let's say Powerball without the Powerball, just 5 numbers, right? If you went to win that lottery, you can get your numbers in any order, all right? So if you choose the correct numbers, but they're not in the same order that they're drawn, they still count. Because, I think it's on Dumb and Dumber. It might be one of the, like, dumb remakes of Dumb and Dumber. You guys have watched Dumb and Dumber? How many of you have seen Dumb and Dumber? Not, oh gosh. If you were my age, you would have watched it till you have it about memorized. It was like a Will Ferrell movie. You guys might not even watch Will Ferrell movies like kids used to. But yeah. But Dumb and Dumber is an idiotic movie, but it's kind of funny. And I can't remember if it's in Dumb and Dumber, though, or if this is in one like the stupid remakes, which are not nearly as good as Dumb and Dumber. But one of them says that they had, there's a line in the movie where one of the guys says, I almost won the lottery, but my numbers were in the wrong order. I had all the right ones, but they were in the wrong order, which means he actually won the lottery because the order doesn't matter in the lottery. But anyway, so order doesn't matter in the lottery. We're working our way up, except for if you're talking Powerball, the first 5 numbers, the order doesn't matter, but the Powerball has to be the right number. So you've got like order doesn't matter here, but order does matter over here, which eventually we're going to work up to actually figuring out the probability of winning the Powerball lotteries. Because I appreciate it for its mathematical qualities. I'm generally not much of a gambler because I do not have enough money to just throw my money away. I feel like the more you understand gambling, the less you want to do it. Unless you get to the point where you understand it so well you can beat the system, which I will tell you about because there are some games where, I'll tell you about this later because we don't have time for it right now. We've got to finish notes. But there are some lottery games that have been designed poorly where if you figure it out, you could actually make money playing the lottery. Card counting's one thing and what you're doing is you're constantly figuring probabilities. Like I know these have been played, so now the probability of this happening is now much higher, so I need to do this. And so it's all probability, like storing all that number in your head, all those numbers in your head. Like you have to be really, like I don't think I could card count. I understand probabilities, but I couldn't card count. Nor would I try because I don't want to be beaten up by mob bosses in a back alley of a casino somewhere. Like card counting, it's all probability. That's what they're doing. They're like they're counting the probabilities higher of this, there, whenever. And one I'll tell you about later is like these kids from MIT that figured out this lottery game and made like thousands and thousands of dollars. I'll tell you about that later because we don't have time for it right now. But it's fairly fascinating. However, most of my knowledge of all of this gambling stuff comes from my interest in it mathematically, not my actual experience gambling, because I do not have enough money to throw my money away. And I'm not, those MIT students, I wouldn't have figured out that I could do what they did on their own. It was pretty high level stuff they did. So anyway, and if I was a gambler, I would lose all of my money. Because whenever my husband and I went to Lake Tahoe on our honeymoon, and we stayed in a casino, and it's on the border of California and Nevada. We stayed in a casino because casinos are cheap. We were in college when we got married, we didn't have any money. We only had the plane tickets because, we had vouchers where we got kicked off of another flight when we went somewhere with my parents. So we stayed in the casino because it was cheap, because they expect you to blow all your money in the casino, so they make the rooms really cheap. And so we did go down to the casino one night and played the penny slot machines, and we gave ourselves $20. And we said we will not spend any more than this $20 because we cannot throw our money away. And it took forever. And at one point we had won $14 on this penny slot machine, and we're like, yes, let's keep playing because we're going to win more. And guess what happened to us? Every cent of our $20 was done by the time we left. I realize this about myself. I must limit myself. I should not gamble, because the same thing will happen that happened to you guys in your bathroom passes. I'll have nothing if I do. So, yeah. But, one of you could have won. There's a slight risk for me by offering that, but not a very big one at all. All right, so 1 through 30. We got to get this done. Sorry. You cannot choose the same number twice. We are going to choose, so if we're doing this without the formula, let's do it just like it's a permutation at first. So the order matters. So you got 30 numbers for the first option. You've got 29 numbers for the second option, because we cannot repeat numbers. We've got 28 for the third, 27 for the fourth, and 26 for the last. Okay, now if I multiplied all that together, that would give me the permutation. That would give me what I would get. We're choosing 5 numbers, right? Oh, 3. Sorry. Sorry, I'm playing Powerball. I'm choosing 5 numbers here. I'm not reading my own question. Okay, so we got 30, 29, 28. All right, that's if order matters, but order doesn't matter. So what we have to do is we've got to divide it by the number of ways that we could put those values in order. So the way that we find that is that, on last time it was pretty easy. There was just 2, right? So you could have 1, 2, or 2, 1. So the way that we're going to find that is we're going to do, so for the first number, let's say now we've picked our 3 numbers and we're putting them in order. So we've got these 3 numbers. They're already chosen. So I have 3 options for whichever one goes first, right? Then how many options do I have for what number goes second? 2. And how many options do I have for what number goes last? 1, right? So 3, 2, 1. It's just the number you've chosen factorial. So if I had chosen 5, it would be 5 factorial. 5 times 4 times 3 times 2 times 1. So if we figure this out, we're going to have, 30 times 29 times 28. See, 2, 4, 3, 6, 0 divided by 6. And so if we divide that by 6, so 4, 0, 6, 0. Okay, so if the order doesn't matter, that increases your odds, but they're still not great in this case, right? All right, so let's look at 6. Student council representatives are chosen for the sophomore class. This is coming up soon, although I think you guys run for offices. But do you guys do representatives for each grade too? I think we do. I'm not sure exactly. I'm not sure exactly how it's. Yeah. So.
You are? Congratulations.
All right. So, if you're doing if you're doing president, vice president, secretary, treasurer, order matters. All right. But if you are doing representatives, the order doesn't matter. You're just picking 3 people. Representative number 1 does not have any more power than representative number 2 or 3. So 4 student council representatives will be chosen. There are 15 people on the ballot. How many different ways can the positions be awarded? Okay. So in this case, order does not matter. So we are going to first do this like order matters. So we have 15 options for number 1. All right. Then we would have 14 for number 2, and then 13 for number 3, and then 12 for number 4. All right. This is if we were doing president, vice president, secretary, treasurer, this is where we'd stop. Although it wouldn't make much sense because you usually run for a specific office, right? But if this were how they set it up, we'd stop. But we want to know the number of ways those could be ordered. So once we've picked our 4 people, the number of ways that they could be ordered, we have 4 options for whoever could be first. We'd have 3 options for whoever could be second. We'd have 2 options for whoever could be third, and 1 option for whoever's last. So we're figuring out 15 times 14 times 13 times 12, which is 32,760. And then we'll divide that by 24. And so we get 1,365. If you would rather use the formulas, you can. In this case, you'd have 15 factorial over 4 factorial times 15 minus 4 factorial. Right, which would be, if you wanted to put it in your calculator, you do 15 factorial over 4 factorial times 11 factorial. Just so you can see how the formula works, because it seems kind of crazy. I just want to, so you would have 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8. I'm just going to put dot, dot, dot. You guys know the idea right here, right? That'd be over 4 times 3 times 2 times 1 times 11 times 10 times 9 times 8, dot, dot, dot. That goes on. So what happens here with the formula is the 11, the 10, the 9, the 8, and so on, dot, dot, dots here, they all cancel out, leaving us with 15 times 14 times 13 times 12, which is what I had when I was trying to just do it logically, over 4 times 3 times 2 times 1. So that's how the formula works. Sometimes if you have really large numbers, it might be easier to use the formula than the logic. But okay, questions? All right. All right, so you draw 5 cards in a poker game. How many possible hands can you get? Okay, almost all. You'll realize almost all of these are gambling related because probability is so much about gambling, you know. It's the perfect thing to use this for. So 5 cards, if you're in a poker game and you're just playing with 1 deck of cards, then as you draw the cards, you don't replace them, right? So you've got 52 options for the first card, 51 for the second, 50 for the third, 49 for the fourth, and 48 for the last one. We'll assume we're not trying to actually deal the cards and try to think of it like that, because that could make it way more difficult. Let's just pretend we're drawing the cards here. So once you've picked those 5 cards, whenever you have a poker hand, it doesn't matter what order they're in. You can move your cards, right? So it doesn't matter which one was first, second, third, or last. So order does not matter here. So you've got 5 cards. You can put them in 5 times 4 times 3 times 2 times 1 different configurations. So 52 times 51 times 50 times 49 times 58 is going to give you, oh gosh, over 120. So take that number and divide it by 120. We get 2, 5, 9, 8, 9, 6, 0. So I'm going to hop over here real quick. I think. Oh, probably. That would start to get really difficult because you know, you got the sides and the colors, and there's more than one color, and yes. But that would get, like, whenever I'm not the world's best at, like, statistics and probability, because when I was in college, I didn't focus on those things, really. Like, my math, like, you can get a degree that's just in statistics and probability. You know, my degree was a math degree, so I had some of this, but not a ton. I had a stats class, and I had one class on probability for statistics and probability. So I did not really go into this really intensively, but you could get whole degrees on figuring this junk out. So it can get really, really, really complicated. So there will be some things, like you might have a situation like a Rubik's Cube. There's no way I'm going to figure that out for you, but you probably could. It would just be a really complex problem. So, you know, probability starts off super, super, super simple. Like, you've got 5 marbles in a bag, 2 are yellow and 3 are red. What's the probability of drawing a red marble, right? Very simple, 3 out of 5. So, like, probability can be super simple, but as you're seeing right here already, it can get much more complicated. Because we've got, you know, this here, we could, you know, make it even more complicated in situations. Like I said when we started this problem, like, if you're actually playing poker, then you would deal the cards. So you, like, if you had 4 people, you got 52 chances for the first, but then, let's see, 1, 2, 3, 4 cards have been dealt by the time they get back to you. So there's really fewer. And then, so I think I could do it, but it'd be harder to do, to figure out, like, the probability. And it would change depending on how many people were playing the game, and, you know, it can get really, really complicated. So, but I think it's all, I really think it's cool, to, like, figure all that stuff out. But, so, yes, you could probably figure it out, but it would not be easy. And I can't do it, so don't ask me to. Coach Wood is actually probably going to be a lot better at statistics and probability than I am, because in AFM you do a little bit, and I think maybe, I don't know, he seems to be better at it than I am, but I'm not an expert. But I know how to do this fairly well. When it gets well beyond this, I'm a little limited. So, all right, very last one, combinations with repeats allowed. So let's say that there are 4 flavors of ice cream: strawberry, chocolate, vanilla, and lemon. You have 2 scoops. How many variations can there be? So in this case, you can get 2 scoops of ice cream. There are 4 flavors. You are allowed to get 2 scoops of the same flavor, or you could get 1 scoop of one flavor and 1 scoop of another. So Brandon, this is applicable to your life right now, right? So you can figure this out. How many flavors do you guys have?
Have like 20 at a time.
Right, but they alternate, yeah. So like, we could, if we were actually using the actual ice cream parlor, it would be much more complicated. We are at somewhere where they've only got 4 options. So, and I specifically chose these because they all have different letters that they start with, so it makes it a little easier to do this. So you could get strawberry and strawberry. You could get strawberry and chocolate. You could get strawberry and vanilla. You could get strawberry and lemon. Okay. You could get, let's do chocolate and strawberry, chocolate and chocolate, chocolate and vanilla, chocolate and lemon. I don't think some of these would be very good, but you could get vanilla and strawberry, vanilla and chocolate, vanilla and vanilla, or vanilla and lemon. You could get lemon and strawberry, lemon and chocolate, lemon and vanilla, and lemon and lemon. Here's the thing. Your order doesn't really matter here unless you really care about which one's on top or not, but your order doesn't matter. So, like, strawberry and chocolate is the same as chocolate and strawberry, so I'd need to mark that one out. And strawberry and vanilla is the same as vanilla and strawberry, so I'd need to mark that one out. Strawberry and lemon is the same as lemon and strawberry. Let's see, we've got chocolate, 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 vanilla is the same as vanilla and chocolate. We'd have to mark that one out. Chocolate and lemon is the same as lemon and chocolate. We'd have to mark that out. Vanilla and lemon and vanilla are the same. So you'd have to mark all of those that are the same out. So in this case, we would have, let's see, 4, 5, 6, 7, 8, 9, 10. We've got 10 options here. Okay, now that had small numbers. We only had 4 to choose from, and we're just choosing 2 scoops. If we actually went where we had 20 to choose from, we're not going to be able to list all of that, all right? Because you would